Hey there, welcome back to Calculus. In this section 2.3, we're going to look at how to calculate limits using something called limit laws, rules of calculating limits. In section 2.2, we got an idea of how you can always estimate a limit by looking at a graph of a function or a table of values, and those are still absolutely among the best tools for getting a handle on what a limit is. But in this section, we're going to learn some algebraic techniques on how you can manipulate them. There's a lot of material in this section, so I've decided to cut it into 3 videos, trying to keep them a little shorter so it's easier to focus on them and watch them. So in this video, I'm going to just rip through a lot of the laws. I've got a lot of material just clipped out of your book, so we can just kind of look at it together and talk about it. The second video, we'll do a bunch of examples. It's just going to be examples. And in the third video, I'll cover the last result in the section, which is something called the squeeze theorem. Okay, so you can see what our agenda is here today. I want to be able to compute limits using these limit laws. I want to tell you what the limit laws are, and then we'll do some examples. There's some certain functions we're going to just want to know how to take limits of: constant functions, polynomial functions, exponential functions. And in particular, we want to be able to take limits of powers and of roots, square roots, cube roots, fourth roots, and so on. Okay, so that's our objective. Let me slide this up here. It's going to be kind of busy. This is taken from your text. But there are kind of 5 primary limit laws to get us started here. So as we're looking at this thing, we kind of have to have a preamble. So the author is telling us that we have some number c, it's a constant, it doesn't depend on x. So c is some constant value. And then we have 2 functions that both have limits. Limit as x goes to a of f of x and g of x both exist. And let's give them some names here. The author didn't do it, but we can write them in. Let's say that this first limit, I'll try to squeeze it in there, as x goes to a of f of x is a number called L. And let's say that, as x goes to a, g of x approaches, say, a number called M. Okay, so f approaches L, g approaches M as x goes to a. And then what do these laws say? Well, they basically say that limits behave nicely with respect to the arithmetic operations. If you're going to add functions together, subtract them, multiply them by constants, multiply the functions, divide, that the limits of those expressions are all going to be carried out by taking the same arithmetic operations, but just applying it to the limits. The only caveat is in this 5th one, the division one. The formula is valid if and only if the limit of g as x approaches a is not 0. So if m isn't 0, then that last one is how it works. So if we wrote these things out in terms of our notation, saying that the limit of f plus g is just the sum of the limits. So it would be L plus m. Take a difference, it's the difference of the limits. You multiply this thing by a constant, you're going to get that constant times the limit of f. So you just get the constant times L. Sometimes students or people like me say that you can pull a constant through the limit. Yeah, so c here is on this side of the limit. You can pull it through. It's kind of a way to remember that formula. Product L times M, or you can just write LM. And lastly, this last one says that this ratio, I'm just going to stretch the equal across that phrase there, it would be L over M, provided that M isn't 0. If the denominator approaches 0, then you can't use that 5th limit law. You have to investigate it maybe with a table or a graph like we looked at last time. All right, let's do a couple of quick examples. You might need to pause and kind of scroll back to this. I can't keep it all visible while we're doing these examples, but I don't have a specific function in mind here. We can view a couple of them. But suppose we have 2 functions, f of x and g of x, and I just picked an L and an M. I'm taking the limit as x goes to 3, and I'm saying for f of x, that limit is 7. The x has to go to 3 in the second one, and the limit is 5. Okay, so just to illustrate some of these laws, if you wanted to know the limit as x goes to 3 of f plus g, well, that first law, that limit of sum, says that it would be 7 plus 5, or 12. If f approaches 7 and g approaches 5, then f plus g should approach 7 plus 5. I'm not giving proofs of these things. We don't have kind of a rigorous definition of limit to give proofs. And again, for a practical calculus course, we don't really need to worry about that. But it's sort of intuitive that if f is becoming arbitrarily close to 7, at the same time g is becoming arbitrarily close to 5, I mean as x approaches 3, well, then their sum should be getting close to 7 plus 5. It's sort of intuitive. How about this guy? The limit as x goes to 3 of 11 times f of x. Well, it's 11 times the limit of f of x. That's 11 times 7, and that should be 77. I think I've got one more down here, a fraction. The limit as x goes to 3 of g is 5. That's not 0. So that fifth limit law that just kind of scrolled out of view says that this limit should be 7 over 5, or 7/5. All right. So you can take limits kind of term by term across sums, differences, products, constants come out, even fractions. The limit of a fraction is the fraction of the limits, is what the last one, the fifth property says, provided the denominator is not 0. Okay. So that's our first 5 limit laws. Let's look at some more. I'm just going to kind of pound these things out at you guys as we go here. Property 6 is kind of handy. It says that if you're taking the limit of an nth power of something, the nth power of f of x, you can take the limit of f of x and then raise that to the nth power. Right? So again, if f has limit L, then the limit of f to the n is just L to the n. These 7th and 8th properties out of your book, they're not really limit laws, they're just kind of facts that if you take a constant function, a function whose outputs never change, and you ask, well, what are the outputs of that constant function doing when the input's near a? Well, the outputs are near what they always equal, they're c. Likewise, if you take the function, think of the graph y equals x. You take the limit as x goes to a of the function x, well, you're going to get a. Yeah, so those are just sort of intuitive limits. You could make tables, graphs. How am I going to use them down here? Well, maybe to combine them. If I wanted to use this power law, if you wanted me to take the limit as x approaches 2 of x cubed, well, the power law, if I wrote it out in symbols, it says I should take the limit as x approaches 2, of x, and then just cube that. That's the power law. The limit as x approaches 2 of x is 2. That's what the 8th property up there says. So we should take 2 and cube it. That is, we should get 8. Any polynomial will work like this. In my second example, sub-example here, I've got this polynomial 3x to the 5th minus 4x cubed plus 11. Well, I'm going to take the limit as x goes to 1. I'm going to do it term by term. The sum and difference laws say I can think about those things one at a time. There's constants in front of it. This 3 is multiplied by x to the 5th. Well, constants come through limits. Subtract the 4 times x cubed and so on. So I won't write it out the same way I did the first example. That this limit is basically found by saying, well, it's going to be 3 times 1 to the 5th, because that's the limit as x goes to 1 of x to the 5th, minus 4 times 1 cubed, plus 11. And now I have a little arithmetic problem to do here. I have to take 3, subtract 4, and add 11, and I think I'm going to get 10. Yeah. So that'll work for any polynomial. What's a polynomial? A polynomial is an expression like this. It's got whole number powers of x, no negative exponents. Whole number powers of x are constant terms, multiplied by numbers and added and subtracted together. So any polynomial looks like that. In fact, if you think about what we did, we evaluated this limit just by plugging in the value 1. Yeah, we just evaluated the limit by evaluating the function. Any polynomial will work like that. The limit laws say it's so. A couple more here. The 9th one here is just summarizing what we just said. The limit of x to the n is a to the n. So it's sort of a special case of the power rule. And in fact, the power rule, I mean, n makes me think of a whole number. It doesn't have to be. This is the nth root. The nth root is just a power of x, right? The nth root, if I write it over here, do you remember from your pre-calculus class, if someone's taking the nth root of x, that's just x to a certain power. Can you pause the video and think about what power it is, like the square root? What is the square root's power? It's just the half power. So in general, the nth root is just x to the 1 over n. So really, the author didn't state, well, the author's stating here that he means n is a positive integer, but the power rule actually works for any exponent. So in some sense, rules 9 and 10 are the same. I didn't pre-cook up an example, but if you wanted to, just to sort of take some of the sting out of this, like if someone was asking you to compute the limit, I don't know, as x goes to 16 of the square root of x, well, this thing says that you can just take the square root of the limit as x goes to 16 of x. That is, you can take the square root of 16. So you're going to get 4. There's an example. illustrating that root law that the author's saying. The function doesn't have to just be x, it can be any function. And these caveats are just reminding us that we're not supposed to take square roots or fourth roots or even roots of negative numbers, okay? So all of those things basically say lots of limits you can just evaluate by evaluating the function. If you have a polynomial, or maybe you remember what a rational function is, a ratio of two polynomials, and as long as it makes sense to plug a in, that is, in the rational function case, there's no denominator becoming zero, a is in the domain of your function, then the limit as x approaches a of f of x is just f of a. So you can just evaluate the limit by evaluating the function. The author is calling that the direct substitution property. Let me illustrate with one of those. I've got a rational function down here, x squared minus 6x plus 1 over x minus 5, and I'm taking the limit as x goes to 7. So basically, the first thing I check is, well, does plugging in 7 make the denominator equal to 0? I'm asking the question, is 7 in the domain? And here, when I plug in 7, it makes the denominator equal to 2. So yes, 7 is in the domain of that function. So the direct substitution property says that we can just evaluate this thing by plugging in 7. So again, I've given myself a little bit of an arithmetic problem to do here. I have to take 49 and subtract 42. 49 to take away 42 is 7, and add 1, that's 8 in the numerator. 7 minus 5 is 2, and 8 over 2 is 4. I should have been actually kind of suggesting this along the way. If you have a Desmos window open, graph these functions, each one of these things. When I do my examples in the next short video, where we're just going to rip through some examples, I've got some graphs ready. But if you graph this function, x squared minus 6x plus 1 over x minus 5, you'll see that when the x coordinates are very close to 7, the y coordinates are going to be very close to 4. Right? In fact, f of 7, that function, if this is the function f of x, the f of 7 is 4. Nice. Okay, so one more property in this, what I hope is a shorter, more focused lecture for you to watch, and it's super useful. In fact, I think it might be the most important property that we've spoken about here today. It's a little bit subtle, but let me try to walk you through it. If you take two functions, f and g, okay, and they absolutely equal each other, except for possibly when x is equal to a. Right? Because limits don't depend on the value of the function at a, they only depend on the values near it. So I have two functions that are equal to each other except for possibly when x is a, then they have the same limit at a, as long as one of those two limits exists, right? So that seems like kind of an abstract thing, like who would care about that? Let me show you how you use that in this example, this fourth example. So here I've got this function x squared minus 9 over x minus 3. And I'd like to try to do it just like we did our previous example. I think, well, is 3 in the domain? Can I plug 3 into the denominator without dividing by 0? And here the answer is no. I cannot evaluate this limit by just evaluating it with the direct substitution principle because I can't divide by 0. Notice that the numerator is also 0. These are the most interesting kind of limits. Ratios where both the numerator and denominator are approaching 0. If the denominator is not approaching 0, yeah, like in our previous example, if this denominator is not approaching 0, then you just evaluate the limit by plugging in. If the denominator approaches 0, but the numerator doesn't, then this is going to be an infinite limit. It's going to be positive infinity or negative infinity, right? You're going to have a vertical asymptote there. So it's these so-called 0 over 0 limits. I'm going to write it with some quotation marks so you don't think I'm dividing, but this is called a 0 over 0 limit. Both the numerator and the denominator are becoming small. When a denominator becomes small, that makes the fraction want to be big. Yeah, dividing by smaller and smaller numbers makes ratios large. The numerator becoming small makes the fraction want to be small. So these are sort of opposing forces here. The question is, well, who's going to win? What is this limit? Maybe it doesn't exist. Maybe it's 0. Maybe it's something in between. Okay, well, I'm talking a lot and I'm talking fast. Let me show you the technique that we're going to use here. Maybe you've already done it while I was talking, but you've probably noticed that numerator factors. the expression x squared minus 9 factors into the expression x minus 3 times x plus 3. The denominator I'm just kind of bringing along for the ride. And now I'm going to use this useful property. So this function, x minus 3 times x plus 3 over x minus 3, it agrees with the following function. For all values of x, except for x equals 3. So in other words, I'm just canceling that common factor. And I can cancel that common factor as long as x is not 3. If x is 3, I would be canceling 0 over 0, which is meaningless. But if x isn't 3, then that number is not 0. And when you divide it by itself, you get 1. So this expression, which I'm just going to kind of circle with the laser pointer here for a second, that expression, if that's my f of x, it equals g of x for all x except for x equal 3. Okay, so this property that you can still see on the screen says that those things have the same limit. And the function g of x down here, the x plus 3, that's polynomial. That limit I can do just by evaluating, by plugging in. So the original limit is equal to 6. So this is going to be one of our very common techniques when you have a 0 over 0 form in a rational function. You're going to factor the numerator and denominator, canceling that common factor, and then taking the limit by direct substitution. Okay, so let's do one more of these examples just to practice, and then we'll end this video. You can take a break, and then I'm going to make another video here where I'm just going to do about 4 or 5, maybe more examples. Okay, let's take it from the top. Taking the limit as x goes to 1. First thing I do is ask myself, well, what do I get when I just plug 1 into that denominator? So you can stop the video here for a second. I'm not going to write it. I'm just going to say it out loud. I would get 1 plus 4, that's 5. Take away 5, that's 0. Okay, so the denominator is approaching 0. So if this is an infinite limit, then the numerator won't be approaching 0. So the next thing I ask is, well, what about that? 1 plus 2 take away 3 is also 0. Yeah, so this thing is also a 0 over 0 limit. So I'm going to try to factor. And in fact, I know what to factor. The fact that 1 is making it 0, if you want a little hint on your factorization, x minus 1 must be a factor of the numerator and denominator. So now you just kind of do your algebra that you've practiced. How do you factor x minus 1 out of x squared plus 4x? Well, you have to put some number here that multiplies to give you a negative 5. So I think it has to be x plus 5. And then you can just check that the middle term works out to be plus 4. Likewise, up here, you'd have to have x plus 3. And now that thing, that expression that we just wrote down in factored form, if x is not equal to 1, that fraction is the same as this fraction. I'm going to just switch color to cancel again, but this cancellation, excuse me, my tongue just left me for a second, is valid provided that x is not equal to 1. But I don't care if x is equal to 1 when I'm taking a limit at 1, because 1 is the one and only value that I don't care about. I just need x to be near 1. Now in this new form, x plus 5 doesn't equal 0 when x is 1, so I can do this just by evaluating. So what do we get? We get 1 plus 3 in the numerator. We get 1 plus 5 in the denominator. That's 4 over 6, or if you like your fractions reduced, that's 2/3. Okay, so that's some of our basic limit laws and a couple of illustrations. I'm going to end this video, and you can check out the next one when you can catch your breath, and we'll do some more examples illustrating how these limit laws can be used to do these calculations. Okay, thanks for listening.